All right, hello and welcome to this Monday night edition um, of our Chem 400 office hours. Um, I can see we got a couple people here on the live stream. There's no pre-programmed agenda tonight. Simply what you want to talk about. A couple comments that I want to make before we start. First, we still have an exam open, so I'm not able to answer questions directly about the exam. We also have our first lab experiment due tonight, and I can comment on that. So if you need help with the calculations, if there's parts of it you don't understand, then I can totally comment on those. I've been slowly working through my emails today, and there are several office hours questions that I have in email. So I will be working my way through those. Obviously, I'm going to give priority to those of you who are attending live. If you have questions, I will answer your questions first. And let's see. Okay, yes, and then the one last thing that I want to reiterate is I will be. Whoa! What in the world? Oh. The opacity's down on my brush. There we go. I will be away from my keyboard from probably like 8:55 to 9:15-ish. My kids are at a thing, and my wife is working a double shift at the hospital tonight, so I have to go just grab them. It's 5 minutes from our house. It won't take long. So if you tune in and you ask a question during that time, just hang on. I'll be back by 9:15, and I will extend our office hours so you won't lose this time. However long I'm away, I will go that much longer. So anyways, just wanted to reiterate that. And all right, we got a couple questions. Okay, let's see here. First question. Meant to email you about this yesterday, but ran into a problem. Yes. Yeah. Totally. So yes, there was sorry. So there were a couple questions that had typos on the exam where, like, for example, you had aluminum fluoride and asked you to find the mass percent of chlorine. There's another one. I think it was like I asked you to find mass percent of chlorine in a compound that only had titanium and oxygen. So I can't alter this or fix it when the exam is live, and it's still live right now. But once it closes, I'm going to be going through the exam, and every student who had that problem, one of those problems with the typo in it, you'll just be given full credit on that problem. So, but I have to manually go in and check everybody's to make sure to see who had it, and then those who did, I will be crediting you for the full amount of points. I can't remember. I think it was like a 2-point problem or something like that. So, anyways, my apologies if you were one of the students who pulled that. I think there were 3 problems like that in the problem bank. So not everybody got them. Yeah, totally. But you do not need to worry about, it's like, I didn't know what to do. You're going to get taken care of. Totally. Dude, you are so welcome. And thank you for your understanding. All right, Hannah, question about the lab. Should the calculations of the mass of NaCl dissolved be the same for part A and B? It asks for it twice for each one, so I just want. Okay, Hannah, excellent question. here's the thing. So it asks for it each time because you need it to calculate the mass percent for each solution. But here's the cool thing about experiment 1 in this particular mass calculation. The mass of NaCl in each aliquot will be the same if this is an important if the aliquots were taken from the same solution. So if both the aliquots are taken from solution 1, they'll have the same mass of sodium chloride. If both the aliquots were taken from solution 2, they'll have the same mass. Aliquots from solution 1 to 2, those will have different masses, but as long as you're talking about the same solution, the mass will be the same. Hannah, great question. All right, Amanda, for the percent mass, should there only be one significant figure? Oh, Amanda, excellent question. Excellent question, an important question, because this will affect the sig figs in your calculation. If you look at the equation for mass percent, it will equal, in this case, it's grams of NaCl over grams of solution times 100. All right. Now, when you look at this, both the mass of NaCl and the mass of solution, both of these quantities are measured. And because they're measured, that means we have to pay attention to the sig figs. But this 100 right here, this is not measured. All right, this 100 is based on the definition of a percentage. No measured. How about not measured? It's based on the definition of a percent, so it will not limit your sig figs. All right, Hannah, you are so totally welcome. Okay, so Amanda, that was your question. Eric, let's see, can I do an example on how to do the percent mass for the aliquot on the lab? Yes, Eric, I absolutely can, and it's actually good timing because we have the equation for percent mass up. All right, so so let's do an example. Percent mass in an aliquot. All right, so I'm just gonna write an example. So this, I'm making these numbers up. So if they turn out to be kind of weird or large, it's because they're fresh. Amanda, you are so totally welcome. Okay, so let's say that 8.6400 grams of NaCl are dissolved in 100.00 milliliters of water. The mass of a 20 mil, so 20.00 milliliter aliquot of this solution was found to have a mass of give me 1 second. Was found to have a mass of 22.1680 grams. Determine the percent mass of the solution. All right. So the first thing that you want to do whenever you're facing something, any quantity, any problem, any calculation that you don't know exactly how to do off the top of your head. If you read this and you're like, I know what to do, go ahead and do it. But if you don't know what to do, then you want to first figure out what you're trying to find. All right. And that is right here. We're trying to find the percent mass. Anytime you're being asked to find something that has a corresponding algebraic expression, write that equation down because it usually will be a roadmap to solve the rest of the problem. So percent mass is going to be equal to the grams of solute, NaCl, over the grams of solution. All right. Now here's where things get a little dicey. We're told that 8.64, so sorry, getting a little bit ahead of myself. Once you know what you're trying to find, now we do. Next, we have to figure out what have we been given. All right, what have we been given? We've been given that 8.6400 grams of NaCl were dissolved in 100.00 milliliters, and we're told that 20 milliliters of this solution has a mass of 22.1680 grams. All right. Now, this right here is our mass of solution. Oh, hang on. We've got a very important part of the percent mass, right? We need to multiply this thing by 100 if it's actually going to be a percentage. There we go. So we've been given the mass of solution. All right, the problem is we need to know how many grams of sodium chloride were in the 20 milliliters, and that is going to be different than this 8.6400 grams of sodium chloride because that's in 100 milliliters, right? We need to know how many grams of sodium chloride are in 20 mils of that solution. Now, here's the cool thing. We know the ratio between the volume of the aliquot and the total volume of the solution, right? This ratio, 20 mils to 100 mils is 1/5. We used 1/5 of the solution, which means that we only used 1/5 of the mass of sodium chloride. So we can take that 8.6400 grams of sodium chloride, and we can multiply this by 1/5. So 8.64 times 1/5 comes out to be 1.728. Let's see, sig figs, we need one more zero. Grams of NaCl. All right, and that will be our numerator. All right, so now, revisiting again our equation for percent mass, it's grams of NaCl over grams of solution times 100. Our grams of NaCl is going to be 1/5 of our total mass of NaCl, so that'll be 1.7280 over the total mass of solution, which is, where was that? There you go. 22.1680 grams times 100. And now we can crunch our numbers. So let's see. 1.7280 divided by 22.1680. The value, then times 100. It's an important thing. So the value, the correct value is going to be 0.7950198. It keeps going. Oh, Eric, you are totally welcome, dude. Thanks for dropping by and adding that question to our conversation. So let's look at how many sig figs we can keep. Our numerator has 1, 2, 3, 4, 5. Our denominator has 1, 2, 3, 4, 5, and 6. So we got to roll with the fewer, right? We're doing division. We can only keep 5, so we can count off 1, 2, 3, 4, 5. This one rounds down, so our final answer will be 7.7950%. And again, this is the percent mass of NaCl with numbers that I've made up for an aliquot of a solution. The cool thing is, in this experiment, all the aliquots are 20 milliliters, so you'll always take that total mass of sodium chloride and multiply it by 1/5. All right, Sean, thank you for being patient. I finally worked my way down to your question. Let's see. Just wondering, is the score we see on the result for the exam right now set in stone? Possibly. It possibly is. But I can't. Here's the only reason why I can't say with certainty. So, Sean, the exam you just took had no free response questions, which means that Canvas immediately grades it when you're done, and so it's instantly graded, so it shows you your score right then and there. That being said, the reason why I can't say with 100% certainty is there were a handful of problems that had a typo in them, and so for those students who pulled that problem out of the problem bank, those students are they received a 0 on that problem because they probably got it wrong because of the nature of the typo. they weren't able to complete it. And so for the students who pulled that problem, they're going to receive full credit on it. So if you pulled one of the flawed problems, and I need to go through and look, I think there's like 3 of them that I'm aware of, and I'm going to do some more analysis after the fact to see if there's any more. If you pulled a flawed problem, you may see a slight bump. The problems with typos, I think, were worth about like 2 points. So there may be a 2-point bump coming your way. But if not, if there were no typos with the exam that you took, then the score that you see is the score that you got. Amanda. Totally correct. Totally correct. Multiplying by 0.2 is the same as multiplying by 1/5. Sean, you are totally welcome. Kiev. Oh. I did. It always takes YouTube a little while to process the video and put it onto the site properly. So we did lecture earlier. It's usually not up by today. Usually by the next day it is. But it first arrives in the channel playlists. So check out... Amanda, you are totally welcome. So yeah, Kievo, I would totally check out our channel playlist. Let me see if I can just grab the link really quick. Oops, no. Let's see the full playlist. Yeah, because on this playlist, dude, you're welcome. It was visible to me, but sometimes I'm not exactly sure what you guys can see, because I'm also the admin for the page, so I can go in and edit a video before it's officially posted. So I don't know if it'll be visible to you, but it will totally show up there before it shows up on the main page. Awesome. That is excellent. Excellent news. All right. Okay. Sorry. New question. Right. Just double check since it just dropped in. Yeah. Yes, Murat. Totally. Here, actually, let me bump back to the previous slide. So I absolutely, yeah. And I actually just a few minutes back walked through. So I just generated some data and a problem where we were given the mass of sodium chloride dissolved in 100 milliliters of water, and then the mass of a 20 milliliter aliquot of that solution was measured, and we were asked to determine the mass percent of sodium chloride for that solution. So yeah, to get the mass of chlorine in that aliquot, because we're taking 1/5 of the solution, in that aliquot, 1/5 of the total mass of sodium chloride will be present. So you divide that mass of sodium chloride, and you and that's what you use for the calculation. You are welcome. All right. Okay, so, and again, just to reiterate, I can totally take live questions, and I will prioritize live questions over over the ones that I have received over email. But I'm gonna start checking my email. Please interrupt me at any moment, because I want to know if there are any new questions. But in the absence of new questions, I'm going to start mowing through some emails. Oh, awesome. Kate, excellent question. I did not have to wait long for a new question. Why is calcium carbonate inorganic? So, the definition of here's the reason. So organic compounds are a diverse class of compounds, but they're all based on they're all what we call hydrocarbons. All right, all organic compounds are hydrocarbons, which is another way of saying they contain both carbon and hydrogen. The reason why calcium carbonate is considered inorganic is because it is made up of a metal cation, namely calcium, and a anion carbonate, which even though it has carbon, it lacks hydrogen, and so carbonate, even though it's very much it's excuse me, structure is very close to a lot of organic compounds because it does not have any hydrocarbons. That's why in general calcium carbonate is considered inorganic. I think you could make an argument that carbonate itself in isolation is organic. You could make an argument, it could get refuted, but when you pair that ion with a metal cation, this is a mineral that's commonly found in the Earth's crust, and so that's really that anion paired with a metal cation. It just possesses mineral qualities, and so that's why it's considered inorganic. Murat, great question. Kate, you are welcome. Murat, here is why you should use 4 sig figs with the calculation, and not 1, even though 20 milliliters was the volume given. So again, this is experiment 1. The 20 milliliter aliquot this measurement part of what this lab was about was analytical glassware, and there were videos to watch on it, and they spent a lot of time talking about analytical glassware and volumetric glassware, and these were measured. And I realize it's an E-lab, so technically we didn't measure anything, but they would have been measured with a volumetric pipette. Oops. Should be measured with they would have been measured with a volumetric pipette, and volumetric pipettes are precise to the second decimal place. All right, they're precise to the second decimal place. And so as a result, these volumes that are measured aren't 20 mils, but they're actually 20.00 milliliters, which have 4 sig figs. It's also why the 100 milliliters was measured, in a volumetric flask. And so it's not 100, but 100.00 milliliters, which has 5. So that's the reason why, because part of this lab was an introduction to volumetric glassware, and the volumetric pipettes measure volumes, measure 20 milliliter aliquots with 2 decimal places out the other end. You are welcome. I do not mind. Just give me a minute as I log in. I do not mind at all. Oh, whoops. Oh, my bad. No, that's not the course I want. All right. Oh, Tatiana, that is not a dumb question at all. So Tatiana, the reason why we multiply the total mass of sodium chloride by 1/5 is because we're using a 20 milliliter aliquot of a 100 milliliter solution. So the I should say where you use that 100 milliliters in the calculation that's where the 1/5 comes from. It's only because your total volume is 100 milliliters, but we use 20. The ratio between 20 and 100 is 1:5, and that's why you multiply sodium chloride by 1/5. So that's where it comes to play. Let's see. Amanda, I will totally get to your question. It's just that Kate asked the question ahead of you, so I'm going to answer hers, and then I'm going to and then I'll get to yours. All right, okay, let's see. I just finished logging into to my text. All right, let's see. You wanted 40, 44, or 47 dealer's choice. Let me get to them. All right, I'm going to go with 44 because it is a weird little multiple of 11. All right, 44. So this is from chapter 4, problem 44. And the problem goes like this. Iron 2 sulfide oh, you know what? They actually, I was about to write this out and then balance it. They give us the balanced chemical equation. They tell us that iron 2 sulfide, so FeS, which is a solid, reacts with aqueous HCl, which is hydrochloric acid, to produce aqueous iron 2 chloride and dihydrogen sulfide gas. All right, and that's the balanced chemical equation. We're told that our reaction mixture initially contains, let's see, where's that? 4.2 moles of iron 2 sulfide. Wait a minute. Oh, no, sorry, I jumped to the wrong problem. It contains 0.223 moles of iron 2 sulfide and 0.652 moles of hydrochloric acid. Once the reaction has occurred as completely as possible, what amount in moles of excess reactant is left? Okay, this is a great question. So here is the real question. What amount in moles of excess reagent is left, once the reaction is complete. All right, so this is really an alternate form of a limiting reactant problem. All right, and we have in lecture focused on the limiting reactant. All right, but what this problem is doing is it's asking us about the one with stuff left over. So here they're asking about the excess reagent. All right, and the excess reagent, the easy way to remember it is not the limiting reagent. It's the other one, the one with stuff left over. All right. Now, when you think about what's going down in this problem, all right, using our chips and salsa analogy, one of them's going to run out, right? Let's say we're eating chips and salsa, we run out of salsa. The chips that are left when the salsa runs out, those are in excess. We had extra of those. And that's what it's essentially asking about. So to solve this problem, we need to do a few things. First, we need to determine the limiting reactant and excess reactant. All right, we need to know which is which. Second, we need to determine the amount of excess reactant that is consumed. All right. And then 3, determine the limiting reactant, determine the excess reactant, determine the excess reactant that is consumed. And the third step is we subtract the amount of excess reactant consumed from the initial amount. Right? Because we started with a certain amount of excess reagent. Once we subtract what's consumed, the leftovers will be the amount in excess. All right? So that is conceptually how we're going to attack this problem. Where we need to start first is we need to figure out what is the limiting reactant. And so to do that, we need to identify the limiting reactant so that we can identify the excess reactant. To do that, we need to take our initial quantity of each reactant, convert it to some product, the same product. I'm going to convert both of these to moles of iron chloride. Oops, sorry. If I want to convert to moles of iron chloride, it should be in the numerator. We should have iron 2 sulfide in the denominator. And this is a 1-to-1 molar ratio. So moles of iron 2 sulfide cancels. And so we find that we would produce 2.23 moles of iron 2 chloride if iron 2 sulfide is the limiting reactant. To determine if that is the case, we need to do this same calculation with our other reactant, HCl. So we need to convert from moles of HCl to moles of iron 2 chloride, because we just got to be consistent. We could pick either one, but now we have to go to the same product. This is a 2 to 1 mole ratio. Now moles of HCl cancel. So we get to divide 0.652 divided by 2 is 0.326 moles of iron 2 chloride. All right, so now that we have these two to compare side by side, we see that the quantity that comes from iron sulfide is smaller, so this is the limiting reactant, and because the amount that would come from HCl is larger, HCl is the reactant that is in excess, or the excess reactant. All right, so we've done step 1. Now we have to move to step 2. So step 1 is locked and loaded. We determined, we determined the limiting reactant and the excess reactant. Next, we need to determine the amount of excess reactant that is consumed. All right, we have to determine the amount of excess reactant that is consumed. And to do that, all right, to solve this, we need to take the way you find how many moles of excess reactant react in this reaction. You have to take your amount of limiting reactant, which is 0.223 moles of iron 2 sulfide, and you need to use the molar ratio of the balanced chemical equation to convert from iron 2 sulfide, your limiting, to HCl, your excess. Again, we're dealing with a 1:2 ratio. 1 mole of iron 2 sulfide will consume 2 moles of HCl. So moles of iron 2 sulfide cancel. We're ready to crunch our numbers. 0.223 times 2 comes out to be 0.446 moles of HCl. And this is critical, are consumed. It takes 0.446 moles of HCl to fully consume 0.223 moles of iron 2 sulfide. So, looking at this again, we have just determined the amount of excess reactant that is consumed. The last step of this problem is to subtract, hang on, I was writing on the wrong layer. There we go. Whoops. So we have determined the amount of excess reactant that is consumed. The last step is we need to subtract the amount that's consumed from the initial amount. So the last step to determine the excess reagent that remains is you take your initial amount of excess, subtract the consumed excess reactant, And when you do, you'll be left with the remaining excess reactant. All right. Well, our initial amount of excess reactant was 0.652 moles of HCl. The amount consumed, we just calculated, was 0.446 moles of HCl. And when we take the difference, we get 0.206 moles of HCl. So this is the amount of excess reagent that is left. All right, so that is how you do that problem. All right, Jared and Sarah, I totally see your questions. Kate just had one more, number 56, so let me do this one more practice problem, and then I will get to you in order of appearance. Thank you. All right, let's take a look at number 56. All right, what is the okay, this is cool. This has to do with what we were actually talking about in lecture today. So it's always fun when that happens. So this is chapter 4, homework, problem. Where's that sucker? Problem number 56. Yeah, totally. Kate, I will totally hit up 58 after I get to Jared and Sarah, but I'll finish 56 before moving on. So let's see. So 56 asks, what is the molarity of chloride in each solution? All right, and then they proceed to give us a different ionic solution every time. So the first one is they give us a solution of 0.200 molar NaCl. All right, and to do this problem, we got to do a couple things. First, you want to write out the equation for the dissociation of whatever solute you're talking about. So here, NaCl will separate into aqueous sodium cation and aqueous chloride anion. The reason why you want to do this is because writing out this equation establishes visually the molar ratio between your ionic compound and the free-floating ion that you're being asked about. Once you've done this, you want to rewrite your molarity. Remember, molarity is moles of solute, NaCl, per liter. Rewrite your molarity with the numerator and denominator, and then use the unit conversion from your dissociation equation to figure out what your molarity of chloride will be. Here, it is a 1-to-1 molar ratio. Moles of NaCl cancel. And so it turns out that a 0.200 molar solution of sodium chloride will have a concentration of chloride ions that is 0.200 molar, because that's moles of chloride over liters. That was part A. Let's look at another solution. They give us 3. B. Our solution is a 0.150 molar solution of strontium chloride. Again, step number 1, take that solute, whatever it is, and write out an equation for its dissociation. Here, strontium chloride will separate into strontium cations. You can determine that charge from the periodic table, plus 2 chloride anions. The reason why you know it's 2 is because you have a 2 here. So for this thing to be balanced, you have to have 2 free-floating chloride anions. All right. Now we take our molarity and write its numerator and denominator, so mole per liter. And then we're going to use our dissociation equation to convert from moles of our solute, strontium chloride, to just moles of our chloride anion. And from the dissociation equation, it is the molar ratio is 1 mole of strontium chloride produces 2 moles of free chloride anion. So this solution will have a concentration of 0.300 molar with respect to chloride. 0.300 moles of chloride per liter. All right, working the last solution in this problem, they ask us to find the molarity of chloride in a solution of 0.100 molar aluminum chloride. And this one you'll recognize as the friendly ghost from lecture this morning. Right, aluminum chloride will dissociate into aluminum cations and 1 aluminum cation and 3 chloride anions. Next, we write our molarity of aluminum chloride with both numerator and denominator. And then convert from moles of aluminum chloride to moles of chloride. And this is a 1 to 3 molar ratio. So this solution as well will have a 0.300 molar solution of chloride. That's its concentration. All right, so that is how you handle that. Yes. We'll probably be hitting up solubility rules on Wednesday. Okay, Jared, let me see. Thank you for being patient, by the way. Let's see. Will we always be given the molecular weight in problems regarding molecular weight and empirical formula? Ah, Jared, great question. And the answer is yes. There's no way for you to know what that is on your own. All right, Sarah, let's see. You got a really small percent mass for your unknown solution for lab, but I wasn't sure if that was correct. Sarah, I don't know if it's correct either, but it is totally possible. There were some that were large and some that were small. So the unknowns kind of range all over the place. One thing you could do is, because I know we handed out these data sets in duplicate, is you could maybe check with the other student who was given a the same data set as you, and see if you guys are getting similar numbers. Jared, anytime. All right, let's see here. Kate, you wanted to look at number 58. What volume? Heck yeah. Good luck, dude. Go rock that thing. K58. What volume of ethanol solution contains each amount of moles of ethanol? Okay. This is an interesting problem. Let's take a look. So this is, again, from the textbook homework, chapter 4, problem 58. And they ask, what volume of 0.200 molar ethanol solution contains and this is where things vary each problem. So for the first one, for example, it says contains 0.45 moles of ethanol, which, by the way, ethanol is C2H5OH. I'm going to write that instead of ethanol from here on out. Okay. Now here's how we're going to solve this problem. All right. This is all based around the equation for molarity. You'll notice they ask us what volume. So instantly we're trying to find volume, and they give us both molarity and the number of moles. So we need to solve for our denominator here. To do so, we're going to need to first liberate our volume from our denominator. We multiply both sides by L. And when you do, it cancels from this side, and we get liters times molarity is equal to the number of moles. But then if we want to find our volume, we need to divide both sides by molarity. So we get a new equation that the volume in liters is equal to the moles of solute divided by the molarity. All right, and now we can use this equation to solve. All right. And so when we do, We have our moles, right? We know that we have 0.45 moles divided by our molarity is 0.200. And again, I'm going to break this down into numerator and denominator, mole per liter. The reason why is you can see that moles here will cancel moles, leaving us with liters as the unit. So 0.45 divided by 0.2 gives us a volume in liters that, well, the volume is 0.25, but you can only keep 2 sig figs because you got 2 in the numerator. You've got 3 in the denominator, and in division, you can only keep the smaller of the 2. 5 is going to round up, so our volume is 2.3 liters. I should say. That is the correct answer with the correct units and the correct sig figs. Sarah and Amanda, just to let you know, I totally see your questions. I'm gonna finish working this one, and then I'll move on to each question in order of appearance. All right, so let's take a look at the next problem. They tell us that we have, where's 58? 1.22 moles of ethanol. And again, we're going to use the same equation where volume is equal to the moles of solute divided by molarity. So we have 1.22 moles of solute divided by 0.200 moles per liter. Again, moles cancel, leaving us with a volume in liters. So 1.22 divided by 0.2 is 6.10 liters. And you'll notice the denominator has 3 sig figs, the numerator has 3 sig figs, and 6.10 has 3 sig figs, so this is our answer for part B. Looking at part C, they want us to do this calculation with 0.012 moles. Again, same equation, just a different amount of moles in our numerator. But I'm still, and I'm belaboring this on purpose, I always break molarity whenever I'm doing math into its numerator and denominator, for clarity's sake. Moles cancel. 0.012 divided by 0.2 is, my calculator tells me the answer is 0.06. My numerator has 2 sig figs. My denominator has 3. So my answer must have 2, but right now it only has 1. So I need to add a 0 to the end so that it has 2. So 0.060 liters is the volume of a 0.2 molar solution of ethanol that contains 0.012 moles. All right, so that is that solution, or the solution to problem number 58. Okay, so Sarah, that is a great question. Let me pull something up here really quick. All right, so pull something up. Oh wait, and I want the worksheet. All right. So here's the thing. So when you plot your data, you're going to get a graph y equals mx plus b, right? So Sarah, this is an answer to your question. Now, assuming that you plotted your data the way instructed to in the worksheet, the worksheet instructs you to plot the mass percent along the y-axis, and it instructs you to plot the density along the x-axis, right? And the way that you calculate, so what you're going to do is you calculate your density right here of your unknown. The way you normally calculate density, it's the grams of solution over the milliliters of solution, right? That is the calculation for density. But then to find the mass percent, because it's an unknown solution, you have no way of figuring out how many grams of sodium chloride are in there. At least the way you did it for your aliquots won't work here because you don't know what total mass was in there. But if you take your equation of the line that you get, y equals mx plus b, and you plug in that density for x and do the math, so multiply your density by whatever that value for m is, and then add whatever your intercept is, this will equal the percent mass of NaCl for the unknown. All right, so Sarah, that is, oh, sorry about that alarm. That is how you calculate the percent mass for your unknown solution. You take the equation of the line, plug in your value for density that you calculated from the mass and the volume, plug in that value, solve for y. That is your mass percent of sodium chloride. Ah, okay, Amanda. No, this is totally fine. Did I miss your question? Oh my goodness, Amanda, I am so sorry for missing your question. Amanda, I'm so sorry for missing your question earlier. But actually, as it turns out, my answer to Sarah's question is actually the answer to your question as well. The way you calculate mass percent for your unknown solution, there's actually no way, based on the data, to determine the grams of sodium chloride in your unknown solution because it's unknown, right? It wasn't given. But you can use the density and the equation of the line from your graph. Yeah, dude, you're so welcome. To get there. You are so totally welcome. And thank you for your understanding as well. I'm usually pretty good about spotting questions in the feed, but every once in a while, I'll miss one as things scroll up and I don't address it, and so you never need to be bashful about repeating a question, especially if it's a question that I have not answered. Because you deserve it. You deserve the answers. And I sometimes need the reminders. Okay. Actually, I'm just going to leave that up there for now because I think it'll be useful. I can totally take any new questions. I'm also going to every time this has been like the magic button so far. Whenever I open Outlook, that's when a new question comes crashing in. So. Yeah, man, fire away. What question do you have? Let me see if I can pull that guy up. He was down there a little ways. Is this it? Yeah, there we go. Dude. Dude, you are 100% correct. That is like ninjutsu level sig figs skills when you can catch the instructor in a in a sig fig error. You are 100% right. That it should be rounded to 4 because that 1/5, as you so aptly pointed out, is a number that has 4 sig figs. So yes, you are 100% correct. Excellent catch. Dude, thank you for improving the quality of this broadcast. Oh, let's see, Eric. I just saw your question pop up. Ah. All right, Eric, so you will need to use the equation of the line from your graph and the calculated density of the unknown solution to determine its percent mass. I just pulled up this slide from a little earlier. So if you plotted your graph the way that the worksheet instructed you to, then you put your percent masses along the y-axis and your density on the x-axis. And then you get this equation of a line, y equals mx plus b. You can calculate the density because you're given the mass of a 20 milliliter aliquot of unknown solution, right? So divide the mass by the milliliters, and that gives you density. When you plug that density in right here, you plug that density into the equation of the line that you get from your spreadsheet, and then solve, right? Multiply that density by the slope, add the intercept. That will give you the percent mass of the unknown solution that you're dealing with. And that is actually the whole point of making the graph, so that you can use the density of the unknown solution to calculate the mass percent. Does that make sense? Ah, yes. All right, just to let everybody know, I am stepping away from my keyboard. I will be back. I'll be back around 9:15 to 9:20-ish. Kyle, thank you so much for your patience. I am back. All right, let's take a look. Let's take a look at your question. Okay, so when calculating the percent, I don't know why when calculating the percent mass of an aliquot, do you use the unrounded mass of sodium chloride dissolved or the rounded up value recorded into the lab? Okay, so Kyle, when you are calculating the percent mass, and the important thing to remember here is this is the percent mass this percent mass calculation we're basing off of a single aliquot. It's grams of sodium chloride over grams of solution times 100%. All right. Now, this mass of sodium chloride in the numerator, what you're given is a total mass. You're given a total mass of NaCl that's been dissolved in 100.00 milliliters of solution. But an aliquot is 20 milliliters. When aliquot is 20 milliliters, i.e. 1/5 of the total. So the grams of NaCl that you're going to use for your calculation is equal to your total mass of NaCl times 1/5, because there's only 1/5 of that total mass present in an aliquot. Jared, great question. So the way I wrote the exam, I almost said the final. I haven't written the final yet. The way I wrote the exam is there are no free response questions on the exam, so it's automatically graded, and the score that you see is what you get. That being said, however, my some students have brought to my attention that there was a couple problems in one of the problem banks that had a typo in them, and so I need to excuse me. Oh my gosh, I'm sorry. I need to go back through everyone's exam after it closes and look to see who what students pulled those problems from the problem banks, and anyone who pulled a problem with a typo in it is going to get full credit for that problem. So theoretically, in a perfect world, you would see the exact response, but there's a chance that we're given a problem with a typo on it, and if that's the case, you might be seeing a small bump, like a 2-point bump, depending upon how much that problem was worth. So there's the very long, wordy answer. It's probably, the score you see is probably what you get. That being said, there may be a bump happening in the next day or two as I comb through those. All right, Kyle. Okay, so you did that, which came to, oh, I see. Okay, but because of sig figs, you lose. Okay, don't know. Okay, Kyle, sorry. I am totally tracking with your question now. Okay, so here's what you do. So, so Kyle, here, let me see. All right, so we have 8.6322 grams of NaCl, and when we multiply by 1/5, it's really, we're multiplying by 20.00 mils over 100. Right, this is where the 1/5 comes from. When you do that, this is where you get that number 1.72644. And what you want to do is you want to use this number unrounded, but you want to keep track of how many sig figs it should have. Your initial mass has 5. The 100 milliliters also has 5, but the 20 milliliters only has 4. So this number only has 4 sig figs. Now what you want to do is use the unrounded number in your calculation. But remember, the number of sig figs it should have. Yeah, Kyle. So yeah, it sounds like you totally got one of the typoed problems. That will be corrected. I just have to manually go back through everybody's exam, so it may take a little while to move through, but I will get there. All right. Totally, Jared. Totally. Okay. Sammy, let's see. Professor, for lecture, since you said we won't be the grade weight. Sammy, that is a great question. And I have actually been thinking about that myself. Soon. All right, Rin, let me see. I'm not sure if we're allowed to ask questions on the experimental quiz, but I was wondering why the question the volumetric flask measurements had an answer involving a volumetric pipette. So, Terry's great question. I just switched the slide because a student, I don't know, maybe 5-10 minutes ago had the same one. So the thing is, and as you can see here, you calculate the mass percent by taking the grams of sodium chloride, dividing it by the grams of solution. Now we're doing this for an aliquot, right? The problem is what we're given the total mass of sodium chloride in 100 milliliters. But one aliquot is 20 milliliters, in other words, 1/5 of the total. So the grams of sodium chloride that you need for the calculation for mass percent is equal to that total mass of sodium chloride multiplied by 1/5, because you're using 1/5 of the solution of the whole thing. So to get the grams of sodium chloride that go into the equation for mass percent, you multiply your total mass of sodium chloride by 1/5, and that'll give you your numerator for the percent mass calculation. Um, so, Tyrese, question. Do you mean, so this is the equation for how you calculate the percent mass of each aliquot. You do something slightly different for calculating the percent mass of your unknown solution. So, so my question is, oh, okay, Tyrese, no worries. Totally. Okay, here, hang on. There we go. Yo, so Tyrese, so this right here, the numerator for the mass percent, this is the this is the mass of NaCl in 1 aliquot. Oops. All right, so that is the mass in 1 aliquot. So they are two different things, but you use the mass of NaCl in 1 aliquot to then calculate the mass percent. let's see. Okay, Kyle, let's see. You're getting, this is your equation. So Kyle, it looks like plausible. With these types of graphs, the specific equation varies a lot as you move from thing to thing. So with an r squared of 1, it means you've got a very, very tight linear fit, so that's good. And the equation looks like an equation that could totally be yep. That's exactly what you want to do, and the closer your r squared value is to 1, the better the linear fit is. So so it looks totally solid. Oh, let's see, Ashley. Sorry, just saw your question. Actually, I will totally take that into consideration. Each exam is different, and the challenge level for each exam will varies based on the content, etc. One thing that you should expect moving forward is exams will definitely be fast, but what I do to kind of set the speed for the exam to determine the time is after I finish writing the exam, I sit down and take it myself, and excuse me, and I time myself to see how long it takes me to take it, and typically what I see is what I kind of aim for is if however long it takes me to take the exam, I usually take that time and double it, and that's what I set the time for the test at. And that's totally not me. I'm not like flexing or whatever, saying like I took this exam in half the time or whatever. But what I found is what I'm doing when I time myself is I'm literally measuring how long does it take to physically write out and do the test. So I find that if it physically takes me 40 minutes, for example, to write out because I do every problem, I do every step. I'm not doing this in a rushed manner. I'm just seeing how long does it take to physically do the writing. And if it takes me 40 minutes to do the exam, then I give the class 80 minutes to take the exam, because at that point I know that half of that time will be spent like writing, like working the problems, but that gives you half the time. If half the time is spent physically writing stuff out, then the other half the time is for thinking. And I know when I kind of verbally break it down like this, it sounds on paper, it sounds theoretically like this kind of relaxed, calm thing. But I realize that doubling the time that it takes me to write out the exam typically makes for a test that that is challenging for most students and creates kind of a time crunch. So it is a parameter that I'm totally open to. Time is a parameter I'm totally open to possibly tweaking in the future, but as you study, accuracy is important, but speed will also be important as well for these tests. So that's a very long-winded answer, a long-winded way of saying I'm open, but you shouldn't expect time pressure to go away, because it definitely will be part of testing this semester. And I so appreciate you posing your question in a respectful way. I know it's easy to be frustrated at the instructor, because I am the author of the exams, and I just want you to know that I so appreciate you being kind about the way you pose the question. I really, really appreciate your civility. All right, Kyle, let's see. Yep, totally, Kyle. There's okay, let's see. I don't know if I'm overthinking it or not. Thinking correctly for the experiment. Finding density. Are we supposed to use the... Okay. So, David, here's the cool thing for finding the density. The density is the simpler of the two calculations. So my guess is you're probably overthinking it. Density is equal to grams of solution over milliliters of solution. So this is a total mass of 1 aliquot. You only use the mass of sodium chloride when you're doing mass percent. Eric, let's see. Do I know if there are any questions on the lab quiz that do not have? Okay, Ashley, let's see. Ah. Okay, Eric, let's see. Percent mass one really gives an equation. Um, Alrighty, and I'm gonna go ahead and call our office hours there tonight. I went a little longer because I had to pause in the middle to go pick up my kids. I hope everybody has a good night. Good luck on the lab quiz. Don't forget to submit your worksheets tonight. And to any who haven't finished, good luck on exam 1. I'll catch you all